Thank you so much, everyone, for joining us today. We are here with another webinar from Adaptiiv, but today we're pleased to be joined by a special guest from one of our customers, the Clatterbridge Cancer Center in the UK, in Europe. And today we're joined by senior clinical scientist over there, Shauna Nickey-Baird, who her and her team have done some tremendous work on the fabrication methods of brachytherapy applicators. So basically a handmade method versus a digitally designed and 3D printed method. As you can see here on this slide, our software is on the left there, top left, and basically that's used in conjunction with a clinically commissioned TPS to 3D print and create patient-specific brachytherapy applicators or Bolus, or just any medical accessories used in radiation therapy. So on the top right there, you can see a brachytherapy applicator created in our software and then 3D printed. So yeah, Shauna's going to take us through her and her team's work that she's actually presented at Estro last year in April in Milan, Italy. And she also presented the same work in Ireland in June, and most recently in London in last month. So along with many other presentations on the same research. So Shauna's well versed in this, and really looking forward to her presenting. Before we get there, I just want to take everyone who hasn't seen our solution or heard about it, just provide a little overview on what we provide. So as I mentioned on the first slide there, we're an advanced 3D printing software solution. We have 3 modules in our software right now. One for simple or uniform thickness bolus, one for modulated electron bolus, and then one for brachytherapy, high dose rate surface brachytherapy. So you can see there, photon electron treatments as well as brachytherapy can be used throughout our software. We use patient data, so a CT scan from a patient. We actually use that in conjunction with our software to create these patient-specific accessories. So in a world that's transitioning and already moving towards more personalized healthcare, a modern approach using technology that's available now, we feel that we fit very nicely into that, into the way that modern healthcare is shaping. So Shauna will take you through exactly the benefits of that and the features of our software solution and how that works. One important thing that I want to mention about our overall software is that it's regulatory cleared. So really from end to end, we have regulatory clearance with our software, and then a fully validated printer and filament materials used to create these medical accessories. So as you can see here, we have FDA 510K clearance in the US, our CE mark in Europe, in the EU, and approvals in Australia as well as New Zealand, and our QMS, our quality management system, is actually backed by ISO certification. So fully regulated there. The validation, we spent more than 5,000 hours validating the 3D printer you see here on this slide. So that's the Axiom 20 made by Airwolf, 3D out of California. And as well as we validated various filament materials for use with our software and the printer, the whole overall solution. So we really see this as a turnkey solution for those out there looking to adopt and implement a 3D printing software. Really, it's an in-house solution that integrates directly with the clinically commissioned TPS, and it's very simple and easy to use. And it's all done with one piece of software rather than multiple versions of open source software. We've seen many people try a do-it-yourself kind of solution where they're using several different softwares that don't really interact or speak to the TPS. So as you'll see throughout this presentation, there's numerous benefits and advantages to using a solution like ours. So without further ado, I'd like to introduce Shauna to you all. As I mentioned, she's a senior clinical scientist with Clatterbridge Cancer Center in the UK, in Liverpool. And I won't do her any injustice, so I'll let her take over and provide an introduction of herself and what she does. So Shauna, over to you.
Hi there. As Rohit said, my name is Shauna. I'm joining you today from the UK in Clatterbridge Cancer Centre, which is in Merseyside. I'm going to talk to you a little bit about my research that I've done in the past year. So basically, we wanted to compare our current hand formation method for brachytherapy skin applicators to a digitally designed and 3D printed method. So I'm going to talk to you a little bit today about that. And the other thing that I'm going to talk to you about is our future plans. So we're going to use the Adaptiiv system 3D Bolus to create brachytherapy applicators in the future. So here's where we are. So as I mentioned, we're in the UK, near Liverpool in the county of Merseyside. At the moment, if you look at the map on the right, we're down at the most southerly Red Star. That's our main site, and we have a satellite centre in the north. But in May next year, we move into a beautiful new cancer centre right in the centre of Liverpool, and our current centre on the Wirral Peninsula will become a satellite centre as well. And this is what our new cancer centre is going to look like. So we're very excited about that. So at Clatterbridge, we have lots of amazing equipment, including 10 linear accelerators and a full imaging department. But importantly for this talk, we also have a full brachytherapy service, and we recently purchased the Axiom 23D printer. And that's what our 3D printer looks like. So it has it's absolutely huge with a massive print volume, which is great. So just briefly to overview 3D printing generally, because I'm not going to assume any prior knowledge. What is 3D printing? So really what you're doing is just taking a computerized 3D model and printing it up layer by layer. So when I talk about 3D model, yes, this could be something like a CAD model, which you'll get in digital engineering, that kind of thing, where you create something in 3D in a digital format. But more relevant to us, which we see every day, especially in radiotherapy, are 3D models like CT scans and MRI scans. And these 3D models can be printed in exactly the same way. So all we need to do is break them down into transverse slices, and then we can print them one layer at a time using whatever material that you choose. So slicing the 3D model is when we convert it into an .stl format. So you take a 3D model and put that through the software to create your STL file. Then you send that STL file to the printer to be printed. The filament which you insert into the printer is the material that the print will be made in. So you can use really any material for 3D printing in general, which melts at a certain temperature. But the most commonly used ones are things like PLA and ABS, which are both types of plastic. And there are options out there with different characteristics, different levels of flexibility, different density. But for this project, we use PLA. So the filament is inserted into the printer. It feeds through. As it's fed in, the nozzle of the extruder melts the material at quite a high temperature, usually over 300 degrees Celsius. The extruder will move around the bed. It sits with its nozzle on the bed and it moves around in the shape of the slice that you'd like to print. So it's constantly extruding, constantly melting, and then as soon as this hot plastic hits the bed, it cools and becomes a solid. And then for the next layer, the printer nozzle will just move up one level and just start printing the next layer on top. And then eventually you get the 3D print shape that you desire. So with my research, we were looking at implementing this 3D printing solution for brachytherapy applicators for skin treatments. So we looked at the literature, what was out there, is this feasible? And we found lots and lots of studies demonstrating that 3D printing brachy applicators for HDR skin treatments was feasible, yes. And we could even see some examples of where people had done it on a patient case. However, there was no kind of studies looking at is it superior? Is it better? So we wanted to know, compared to our current 3D print, or our current hand fabrication process, which is the way that we make our skin applicators at the moment, would a 3D printing solution be as good or better than what we're doing at the moment? I'll just very briefly talk to you about our current process. So I always say this is a truly multidisciplinary process. We have involvement from our mold room, our clinical oncologists, from physics, CT radiographers, and the brachytherapy team, to get every patient through this process. So basically, the patient arrives on day one, and they will go to the mold room and meet with their clinical oncologist, and they will create an acrylic mask for the patient for the site that they'd like to have treated. We commonly see areas like bridge of nose, scalp, and the backs of hands are suitable areas for this type of treatment. So the patient will have their target outlined by the oncologist, and the mold room team will create an acrylic mask for that area. And then a decision is made by the physics team as to how many catheters they'd like to use. So the catheters are the tubes that will carry the source through the applicator. So a decision has to be made about how many catheters you'd like, and the distance between the catheters, so the inter-catheter distance, and the inter-catheter distance and the standoff distance, which is the distance between the catheter and the patient's skin. So how far away will the source be from the patient's skin? So we do this to get adequate target coverage and dose to the depth that we'd like. And so once we've made a decision about that, we send the applicator back to the mold room team, and they create the standoff using boxing in wax, and they attach the catheters, trying to make them as equidistant from each other as possible. So this is really a very hands-on process, and it takes quite a long time. It can take up to a week to create one of these applicators, which is very time-consuming on our radiographers. So the next step, once we have the applicator, is to CT scan it. We CT scan these applicators without the patient present. So we take the CT and we use that to create a treatment plan, and then the plan is delivered to the patient over the specified number of fractions. And for the first fraction, we have a TLD at the center of the field to get a dosimetric in vivo verification. And that's how we do it. So for this study, we wanted to use real clinical cases. So to be eligible for the study, really all we needed to be was in possession of the patient's applicator. The applicator had to be in good condition, and we went for applicators which weren't too large, but because they needed to be 3D printed, so that if they were extremely large, it wouldn't be possible. But we found with the Axiom 20 printer, because it has such a large print value, that wasn't an issue. So our previous 5 patients were all eligible for the study. These happened to be 4 no-site patients and 1 thumb-site patient. And you can see here in the 2 rightmost columns the specifications for these applicators. So what was the catheter to shell inner surface distance, and what was the inter-catheter distance that we required. So the first step, once we had chosen our patients, was to get some baseline results. So we wanted baseline results for geometric and dosimetric accuracy. So what we did is we took the applicators in their current form through our entire treatment process, from CT scanning to treatment delivery. And we did that using our local precision protocols, but we did it without a patient present. So instead of a patient, we used bolus bags to represent and simulate the patient's presence. For the next step was that we would remove all the wax and catheters from the acrylic mask. We were using the acrylic mask as the base for the 3D printed applicator. The reason we were doing this is because we did not CT scan these patients, and therefore we didn't have their outer contour with which to create the 3D applicators. So instead we used the acrylic mask as a surrogate. So we CT scanned them without any of the wax in place, and then created the 3D printed component of the applicator from that surface. So our goal with these 3D printed applicators was to get the specified inter-catheter distance and the specified shell inner to catheter distance as close to what was specified as possible. And we created the applicators in the Eclipse contouring module, At the time, we didn't have the 3D printed, the 3D Bolus solution from Adaptiiv. So we created it in our contouring, our TPS contouring module. And what we did is we created the main volume of the applicator, and we made that 1 centimeter greater in size in all directions from the target area. And then we used guide structures to show us where exactly the channels needed to be for the catheters to go in. So first of all, we created a standoff guide structure by outlining the interior of the shell and extending that by the amounts specified for the standoff. And then we created a vertical line through the applicator and on each slice dotted on the location of the channel that we'd like. And then taking that original central channel, we created a structure from that, another guide structure, cylindrical in shape, which had the radius, the radius of that structure being the inter-catheter distance that we required. And then wherever our standoff guide structure crossed with our channel guide structure, that would be where we would place the next channel on each and every slice. As you can imagine, then we repeated this until we had the number of channels that we required. As you can imagine, this is very time consuming, but in the end, we created 5 of these applicators specific to our patient's contour. And then all we had to do was 3D print them. So they came out, we exported them from the TPS and DICOM format. We converted them to STL, and then using the Apex software, which came with our Axiom 3D printer, we chose the settings that we'd like to print with. So how the infill density of the applicators and the speeds that we'd like to print at and things like that. We chose those to create a G code, and then the G code was exported to the printer, and we just printed them. And so we actually chose to print with just 20% infill because we didn't believe this would have an effect on the dose distribution, but that it would speed up 3D printing significantly. So our print time for these applicators range from 2.5 hours to 4.5 hours. So here's our two of our finished applicators, one for one of the nose patients and one for the thumb patient. So we found that the applicators, straight away we knew that they were extremely accurate because they fit so perfectly onto the shells and they located themselves really easily. So to fixate them, we actually just had to use a little bit of sticky tape because they fit so well. And then we inserted the catheters. We identified that button-ended catheters would be a really good option for button-ended catheters would be a really good option for brachytherapy applicators. But for the sake of this study, we just used blind-ended catheters and fixated them with a little glue. As for treatment delivery, as I mentioned earlier, we had taken baseline results as reproducibly as possible. So we just took the 3D printed version of the applicator through exactly the same process. For the dosimetric measurement, we placed a TLD at the center of the target area. So we do this for first fraction of treatment anyway, so we just did this according to our normal clinical procedure. As for the geometric measurement, we took the CT scan of the 3D printed applicator. And what we wanted to do was measure from the shell inner to the center of the catheter for each channel on each slice within 5 millimeters of the target area. So that's quite a lot of measurements. And the problem with this is that you have to have, in order to get a measurement with a simple line tool, you would have to measure perpendicularly to the shell inner surface, which would be extremely difficult, almost impossible to do. So instead, the system that we came up with was in Eclipse contouring module, we outlined the shell inner surface, and then we grew various structures of increasing size normal to the shell inner surface. And in that way, you can just look at which line falls closest to the center of the catheter in order to get your measurement. And you can do this quickly on each slice and for each catheter. So we were able to take very many measurements. And we used a similar system when we were measuring the inter-catheter distance. So we took each catheter, outlined it, and then grew that by increasing amounts. And again, we just looked at which structure fell closest to the center of the neighboring catheter. And here are our results. So in total, we took over 3,800 individual measurements. But the problem with this when we were looking at it statistically is that we only had 5 patients. So we looked at the number of individual measurements which were within 1 millimeter of the specified value for both catheter to shell inner distance and inter-catheter distance. We chose 1 millimeter as the threshold because both types of applicator were extremely accurate, both hand-formed and digitally designed and 3D printed. So 1 millimeter was the appropriate tolerance, which is really shows how accurate they were. So as you can see from the graph here, for patient 1, we actually found that the hand-formed applicator was more accurate for intracatheter distance. And for patient 2, they had very, very similar results. However, for patients 3 through 5, we found that the digitally designed 3D printed applicator was more accurate for intracatheter distance. And we see similar results for catheter to shell inner surface distance. And for patient 1, the hand-formed applicator was slightly better. However, for all the other applicators 2 through 5, the digitally designed and 3D printed applicator was more geometrically accurate. As for the TLD measurement, we found that all measurements for both digitally designed and 3D printed and the original applicators, hand forms, they were all within the clinical tolerance of 5% that we use. And so we were confident that both types of applicators were in agreement with the dose predicted by the treatment planning system. And as for the results, statistically, we looked at the proportion of means of these results and found that they were statistically significant in both cases. So that gives us evidence to reject the null, that gives us some evidence to reject the null hypothesis that there is no difference in the geometric accuracy of these applicators. And as for the dosimetry, as I said, we were happy that they were within our clinical tolerance of 5%. Conclusions. So as I said, we found that there was some evidence that the 3D printed applicators were more geometrically accurate. We think this could be a hugely time-saving process because it takes our mold room team so long to create the applicators by hand, and it's a real art for them. So we think if we could get a system that would mean we could digitally design these applicators, it would be hugely time-saving for a lot of our staff. And they're quite cost-effective because the materials that we are printing in PLA, which we use for the study, is are very inexpensive. So once you have your 3D printer, this can be a huge cost-saving measure. They're reprintable, so you can imagine if we take one of our very delicate hand-formed applicators, and during treatment, it accidentally falls on the floor and breaks. You would have to mend the old applicator or create a new one, and that would mean creating a new treatment plan because these applicators are so sensitive to millimeter distances for treatment. They're very professional looking. We've started printing them in black and they look absolutely great. So for our patients coming for the treatment, I think that would be really nice to have a professional looking applicator. And they're quite comfortable for the patient, especially because we've printed them in lower info. So they're quite light and they're quite smooth on the exterior. So I think that would be quite nice for the patient. Future plans. So ultimately, we'd like to implement this clinically. We've purchased the Adaptiiv system, which has a Brachytherapy applicator module, which is really great because it'll save us a lot of time in designing these manually. And we're looking into CT scanning the patient. We believe that there would be some clinical benefit to being able to visualize the depth of the tumor. And if we're CT scanning the patients anyway, we could create their applicators without the acrylic shell at all. So it could be created directly from their CT scan, which would be great because they wouldn't even have to have a mold room visit, which was really amazing for the patient. So now I'm just going to talk to you quite quickly, briefly about 3D Bolus. So we purchased it this year. It has 3 modules: simple bolus, modulated electron bolus, and surface brachytherapy applicator. the surface Brachy applicator is the only one that I'm going to talk about today. But basically, all the structures originate from your treatment planning system. They're exported to the 3D Bolus software. They're converted to STL for printing, and then these designs can be imported back into the treatment plan system for verification, even before printing, which is great because it means that you could start your 3D printing. It means that you could start your treatment plan before the applicator was even done printing, which would be amazing. So for surface brachytherapy, here on the right, you can see applicators which have been created using 3D Bolus. So it's a method that we use to treat superficial lesions that I spoke about. It creates patient-specific applicators with hollow trajectories, so that you can insert your catheters. It's highly customizable, providing superior dose distribution, which is what we'd like to achieve. And so I took one of our patients through the 3D Bolus workflow, so I'm just going to talk to you a little bit about that now. So what we did is we took a patient case. We took a mold of the patient's exterior and then created this clay representation of the patient. We CT scanned that, and as you can see here, we've outlined the target in pink. And then we've created the base of the applicator in our Eclipse contouring system, so our TPS. So we've created this applicator larger than the target area because we're going to create the hollow structures in there to insert our catheters. So next we import it into the 3D Bolus system, and you can see here, you can see our two structures are still there, and you can see all our CT data as well. These are some of the tools that you can use in 3D Bolus, which are very convenient. So you have different tools to find your way around, tools for viewing your CT scan and your structures, and then you also have tools for editing your structures, so cropping, which is very useful, smoothing tool, and my favorite, the patient label, so that you can print the patient's name and patient number directly onto the applicator so that you don't get them confused. So if you see here in the 3D Bolus, we take our RT structure, which we've created as the base of the applicator, and we choose the number of trajectories that we'd like, the inter-trajectory distance, and the surface distance, which is the standoff distance that I was speaking about earlier, and as well the tunnel radius that you'd like. So depending on what catheter you use, you want to choose the appropriate tunnel radius. So all you have to do is choose those numbers, and it automatically generates the trajectories, which should obviously be a lot quicker than the method that I used when I was doing it manually. So it's literally just choosing the numbers and click, click, click. And then when you create these trajectories, it gives you information about if there's areas of high curvature, which may cause source sticking, which is what the greatest risk in brachytherapy, or which might cause the treatment to not be delivered because the treatment unit detects a risk that then source sticking may occur. So it's great that it does this, so it warns you before you print it that it may not work, and then it allows you to adapt and fine-tune your trajectory so you can reduce the curvature of those areas if you believe that the source will not pass through them, which is extremely useful and massively cost-saving, that you can do that at the creation of the applicator. So once you're happy, you can create your trajectories and subtract them from your material, and you have your applicator. So you're ready to export that to your 3D printer. So next, it will go to the Apex system, which I mentioned earlier, where you choose your print settings. One of the really great things about Apex, which comes with your Axiom 20 printer, is that you can choose to save profiles of print settings. So once you have a set of print settings that you are happy with for your brachytherapy applicator, you save that profile and you just import it each time that you want to use it for a brachytherapy applicator. And so there's no need to every single time choose all of these settings, which is really convenient and time saving. And then printing, you just print it on your Axiom 23D printer. This printer comes with various nozzle size, which is great. And we use our smallest nozzle size for printing brachytherapy applicators because we want them to have really good resolution, fit really well into the patient, and that the catheters fit really well into the channels. And there's dual extrusion option, which would be really good for printing overhangs, or if you want to print it to different materials. And there's a heated bed, which is great because you don't get warping in your 3D print. And the print time depends on the size of the printer and the settings which you choose. And that's all from me. I'd love to hear any of your questions.
Well, that's great. Thank you so much, Shauna. That was an awesome overview of the work that you and your team have done on the fabrication of these applicators. Really fascinating to see the results and how many individual measurements that you took. It was a very detailed study, over 3,800, I believe you mentioned. So really promising and positive results, showing that 3D printing and digitally designing these applicators actually proves the hypothesis wrong, and what you were trying to do kind of came to fruition. So great to see that. Thank you so much again. We do have some questions from the audience. Time permitting, we may not get to all of them, but I do want to start with a couple here. And if we don't get to any, don't be discouraged. To everyone out there, we'll follow up with you and provide answers to all the questions that have been asked in an email follow-up after the presentation, and we'll also include a recording of the webinar as well. So Shauna, you talked about densities and printing in different densities. I guess, what are the advantages of being able to do that with a 3D printed brachytherapy applicator versus, and I guess what are the different densities or infill that someone could print at?
Yeah, so it's quite interesting actually because we were interested to know whether, kind of as a sub-study, we had a little look at whether the infill density for, and ultimately the density of the applicators themselves would have an effect on the dose distribution that we achieved. So with most brachytherapy systems, the brachytherapy system will assume that everything is water, and that the patient and all the surrounding area is all water, which is why we use the bolus for backscatter. And that's because the inverse square law is so dominant over attenuation in brachytherapy. So we decided that we would print them almost hollow. I mean, they have 20% infill, and so they have really low density. And that really sped up our 3D printing of these applicators. Some of them we printed in just 2.5 hours, which is really great. And when we looked at the results, so if you look at the TLD results, if there was a huge difference between printing with full infill and printing with just 20% infill, then we'd see a difference in the TLD measurement. So as you can imagine, the applicators at the moment are made of wax, so they have an almost water equivalent density. And our applicators were almost completely filled with air. And yet, when you look at the TLD measurements, they're almost exactly the same. So really that kind of proves to us and gives us that confidence that the infill does not need to be full infill. So that's really great. On the other hand, if you were printing something that was sensitive to attenuation, or greatly sensitive to attenuation, like for bolus treatments, you really would want to be printing in full infill to get that near water equivalent density.
Yeah, good point there at the end on printing bolus with full infill. We've seen that as well. I would imagine as well that the patient comfort with a lighter, less dense applicator would be improved rather than a heavy wax or what they traditionally use. Would that be the find? Yeah.
Yeah, no, definitely. And we brought these applicators down to our brachytherapy radiographers to see what they thought about the new system. And they thought it was absolutely brilliant. They said to us, they're so much lighter for the patient, so they don't have something heavy, especially when we do a lot of patient treatments on the head or on the face. And they also mentioned that they thought it would be a lot less claustrophobic for the patient to have something light on there, and something that would be smaller as well, because we're not using these very large masks, hopefully in the future.
Yeah, absolutely. And I did mention earlier about the different filaments that we validated for use with our solution. So one of those is TPU, thermoplastic polyurethane, which is a more flexible, softer filament. So yeah, even the patient comfort can be even further improved from PLA if you use a more flexible filament like TPU. So.
Yeah, and it would be absolutely great to use TPU, I think, for these type of applicators, especially you can imagine for an area like the nose, and when you're trying to fit it on, if there's been any kind of change in shape because of the disease, it's quite nice to have a little bit of flexibility there for putting on the applicator.
Sure. Awesome. Well, it looks like we have time for just one more question, and again, we'll follow up for the outstanding questions in an email after. But yeah, last question for you, Shauna. What would be I guess, the best advice you give to the center or a facility looking to, I guess, build a business case to really adopt and implement a 3D printing solution for brachytherapy or for radiation therapy in general, radiation treatment?
Yeah, I think when we made our proposition to buy the 3D printer, one of the things that we pointed out was how much time would be saved by staff by implementing this. I think at the moment, when I was doing this study, I had to do it all manually by creating these guide structures and things like that. But as I demonstrated with towards the end of the presentation with 3D Bolus, it really is going to be a kind of click, 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 and you have an applicator approach. So it's really going to speed things up. Whereas at the moment, some of our mold room radiographers are spending hours and hours laboring over trying to get these hand-formed applicators exactly correct. It would be so nice to have something that's a little bit more reproducible and a lot faster to print. I think they're quite cost effective as well. So the idea was that once we had purchased the 3D printer, that the materials to buy would be quite cost effective. So in the long run, we would be that would be quite good as well. So yeah, we spoke as well about how it would be nice to have a solution that would be CE marked as well. There's a real push in our hospital towards CE marking, and I know it has similar clearances in other countries. And so we really wanted something that was CE marked rather than something which we were making by hand, and that was completely being produced in an individual way for each patient. Rather, we still wanted the applicators to be patient specific, but we wanted to have that CE mark to give us confidence as well. Do you have any points, Rohit, that you think would also be good to add to a business case?
Yeah, no, I think you covered it really well, and it's great to hear the firsthand experience from Clatterbridge's point of view. Yeah, I would definitely agree. The things you mentioned, saving time, cost effective. We've actually seen some of our clients being able to completely shut down and eliminate their mold rooms because they have an easy point and click software that takes minutes to create one of these and design one of the an applicator or an accessory versus hours or days, as you've mentioned. Really important. And another thing you did mention actually as you presented was the ability to verify the applicator or accessory in the TPS before printing. So the Adaptiiv software that we offer allows an easy import of the DICOM directly from after you design it in our software back to the TPS to conduct that dose verification. So that seamless integration we feel is a big part of building the business case as well. So yeah, and the regulatory considerations are definitely something that's very top of mind for all centers across the world, especially in Europe now. So yeah, you made great points there. So thank you so much.
It's quite interesting that you mentioned about mold room as well, because what we found in our hospital is that our mold room team are very excited about the 3D printing solution, and they're excited about working with 3D printer and taking our current processes into the future, really.
Yeah, they're able to kind of learn a new skill set in the digital world, I guess, with technology advancing as quickly as it is, you know, so using an innovative type approach that Adaptiiv offers is awesome for them. They get to kind of, I guess, pivot and reassess their career paths and go into a, you know, more digitally tuned focus. So that's great to hear, that they're able to not only use this but also be effective in their jobs as well. So really good to hear. Again, thank you so much, Shauna. Really appreciate your time.
No
I know
problem at all.
it's a busy time of year, so yeah, thank you so much. And again, to everyone out there, thanks for listening and attending today. And for any outstanding questions, we will follow up with answers to those, as well as recording to today's presentation. So thanks again, Shauna.
Thank
Have
you.
yourself a
Bye.
great day. Thanks.